I'm a senior at Marin Academy, and today I'm going to talk about Euler's identity. So there's a man, Leonard Euler, and in the 18th century, he put all these mathematical constants into one equation. And in fact, it's been called the most beautiful equation in math. So if you go to Google and you search the most beautiful equation in math, you will get Euler's equation, or Euler's identity. E to the pi I equals -1, or e to the pi I plus 1 equals 0. And it has these 5 mathematical constants. So we have e, which is the base of the natural logarithm, and it comes up a lot in calculus. It's an irrational number right across the screen right here. And it goes on forever. Pi, which I'm sure all of you know, the ratio of the circumference of a circle to its diameter. Another irrational number, though it's more widely known. Then we have I, which is the imaginary unit. It's equal to the square root of -1. So I times I equals -1. Then we finally have 1 and 0 all in one equation. And there's a quote from Benjamin Pierce that says, "It is absolutely paradoxical. We cannot understand it, and we don't know what it means, but we have proved it, and therefore it must be the truth." And this, ironically, is coming from a Harvard mathematics professor who taught at Harvard for more than 50 years in the 1800s. And I don't really like this mentality because I think that there is an intuitive way to understand it. We just have to think about it in the right way. And in fact, if you go to Google and you look up proofs of this, you get a bunch of Maclaurin series and Taylor series polynomials which look good on paper, but they're not really intuitive. So following Grace, I'd like to go back to the basics and build on analogies that we already know. So to do that, we're going to start with looking at addition and multiplication, and then moving on to exponentiation. And then finally, we're going to look at imaginary numbers and put it all together in the complex plane. So what is addition? Addition is just a translation of the origin, or the point 0. So if we have 2 number lines here, and we want to do the action +4, adding 4, well, that just corresponds with taking the point 0 and shifting it to the right 4 units, so that the point 4, or the point 0, lines up with where 4 used to be. Now we can also flip this and subtract 4. So if we're subtracting 4, we're taking the origin and we're sliding it to the left 4 units, or lining up 0 with where -4 is. We can also have the additive action of +0, which is just keeping the origin where it is. So that's why +0 doesn't do anything. Now let's look at multiplication. What is multiplication? Well, it's just a stretching of the number line. So given our same 2 number lines, if we want to have the multiplicative action of times 2, we pin down the point 0 and take 1 and stretch it to where 2 is. So now we have 1 lining up with 2, 2 lining up with 4, and so on. We can also flip this and squish the number line. So that's a multiplication by 1/2 is taking the point 1 and squishing it to where 1/2 used to be. And that's the same thing as dividing by 2, as I'm sure you guys know. We can also have a multiplicative action of +1, which is just taking the point 1 and stretching it to where 1 used to be. So a multiplicative action that does nothing. Can I skip this? Sorry about that. Okay, so what is exponentiation? As I'm sure you guys know, if we have it's connected up to his computer though.
Have Jamie do it on the computer.
Yeah. Okay, so 2 squared, that's 2 times itself 2 times, We can also look at 2 cubed, which is 2 times itself 3 times. What happens if we have 2 to the 5th? That's 2 to the 2 plus 3. And that is equal to 2 squared times 2 cubed, which is also equal to 2 times 2 times 2 times 2 times 2, 2 times itself 5 times. And that brings us to this general form for exponential equations, which is 2 to the x plus y equals 2 to the x times 2 to the y. So adding the inputs on one side corresponds to multiplying the outputs on another side. So now let's look at the complex plane. So in the complex plane, we have a real axis and an imaginary axis. So if we denote this point 2 plus 1i, that corresponds with going over to the right 2 units and up 1 unit. Is this working now?
I don't think so. But if you click it, I hear it, and then I can
Works for me. Okay. So what is multiplication in the complex plane? Well, to start, let's look at multiplication by I. So to start, we're going to look at the point I to the 0th power, which is just 1. And then if we multiply by I, we get a 90-degree rotation upwards, which brings us to the point I. And then if we multiply by I again, we get another 90-degree rotation, so we're at I squared. And we're at a full 180-degree rotation, and brings us to the point -1. If we multiply by I again, we're down at -1. And finally, I to the 4th power, we're back at 1. So it has a period of 4, and that's why the cycle repeats, because we've done 4 90-degree rotations and we're back at 360 degrees. We can also take I to the 1/2, or I to the 0.5, and that corresponds with a 45-degree rotation, because it's halfway of 90. And so all our multiplicative actions by I correspond to some point on the unit circle, some point on the circle of radius 1 centered at the origin. So now we have 2 points here, our original point 2 plus I, and then we also have the point in the upper right 2 plus I squared, so 2 plus I times 2 plus I. And so going back to our original definition of multiplication as pinning the origin and stretching the point 1, if we pin the origin and stretch 1 to our original point, and then traverse along the new plane that we've stretched to 2 plus I, that brings us to our squared point. So multiplicative actions are still the same in the complex plane. But what happens when an exponent is imaginary? Well, going back to our original equation that is a property of exponents, we can split up 2 to the I to 2 to the 0th plus I, and we get this real component, which is stretching. And then wouldn't it make sense that since our multiplicative actions by I are just rotations, that our imaginary component would just be a rotation too? And that is in fact true. If we look at the point 2 to the I, that we have it's on our unit circle, and it corresponds with 0.693 units of distance across that unit circle. And so 0.693 radians is the angle. And if we increase the base to 5 to the I, we get around 1.609 units of distance across the unit circle. And there's this base, E, which if we have e to the I, that corresponds with 1 unit of distance across our unit circle. And if we multiply the coefficient of I, or if we take the coefficient of I and change that value, that will also change the distance that we traverse along our unit circle. So if we take e and raise it to the pi times I, that corresponds with pi units of distance across our unit circle, which brings us halfway around the circle, or to the point -1, which brings us back to our original equation. And you're probably wondering why e? Well, it has to do with some vector calculus, but in its simple form, e is its own derivative in calculus. So when we take the derivative of e to the I x with respect respect to x, that's just equal to, that's, if we take the derivative of e to the ix with respect to x, that's just I times e to the ix. So it's just a pure 90-degree rotation, whereas if we have some other base, like 2, that's going to be a slightly shorter or a slightly longer 90-degree rotation. But the point of this is to see that when we... I think this works sometimes.
See if it works now.
Okay. That if we take e and raise it to an exponent, or if we take any base and raise it to an imaginary exponent, that's just going to be a rotation. So in our original looking at the complex plane, when we denoted points, we went horizontal and vertical. But in this way, we can think of these points as being an outward stretch and then a rotation along the unit circle. And going back to this original quote, I hope that you can see these exponential points in different ways, and hopefully you can think about these differently and you were able to get something out of this.